Hello everyone, let us continue what we have been doing in last two classes. We are trying to understand what is the matrix method for analysis of truss. Today's topic is again same application of boundary conditions. If you recall the first two classes, the first class we discussed the general concept of analysis of truss. The second class we discussed how to obtain the member stiffness matrices and then assemble them to get the global stiffness matrix. Now, once we have the global stiffness matrix, next step is to applying the boundary conditions. Now, that is what we will be discussing in this class. Okay. So, if you recall, this was the problem that we have been we are trying to solve. This was the truss, and then we have member number, we have different node numbers, say node number 1, node number 2, point of joint number 2 and joint number 3 and the corresponding member numbers. And then once we have these, we determine all these stiffness matrices, then assemble them, and it is the global stiffness matrix. And these 1, 2, 3, 4, 5, 6, they are associated with degrees of freedom in the direction of 1, 2, 3, 4. At each joints, we have 2 degrees of freedom. So, total 6 degrees of freedom, and this size of the global stiffness matrix is 6 by 6. Okay. Now, let's suppose these P1, P2, P3, P4, these are the corresponding forces, P1, these are the corresponding forces, and the corresponding displacements are represented by U. So, E1, P1, E1 is the displacement in the direction of 1, and then P1 is the associated force. Similarly, P2 is the direction displacement in the direction of 2, and the associated force is P2. Now, once this stiffness matrix, what this exactly does is this relates this P1, P2, P3, P4 with this, right. That was this that was the purpose of this stiffness matrix. Now, P1, P2, P3, P4 and the displacement U1, U2, U2 displacement. Okay. Now, if I substitute this stiffness matrix into here, the form that we get is, we will get a form like this. Okay. Now, you see this is the form we get. Okay. Now, what this stiffness matrix essentially gives you, we have been repeating this many times, and probably I will be doing it again and again. If we have a system, and if we apply some force to the system, and analysis of structure is to find out what is the response of the system. So, in this case, the response is the displacement. Okay. So, if we apply a force, then what would be the displacement, and this expression, the force, the stiffness into displacement is equal to force, that is essentially the representation of, or mathematical representation of that system. Okay. Now, there are some properties this stiffness matrix must satisfy. You can closely look this that the stiffness matrix is symmetric. Stiffness matrix is symmetric, which is a direct consequence of the reciprocal theorem, if you remember Maxwell reciprocal theorem. Another thing, the stiffness matrix is all these elements in the stiffness matrix, all these diagonal elements in the stiffness matrix, they are all positive. They are not 0, they are not negative. Okay. The stiffness matrix is all the diagonal elements are positive. Now, but you know, if you try, so what essentially we have to do next is once we have this, if we know what are the forces you are applying to a system, and then if we solve, we need to solve it to get the displacement, right. Now, suppose if we have, essentially then what we have to do is, suppose you have a, so this is a common thing that you have learned in your matrix theory, Ax is equal to b, if we have an equation like this, and then we have to, as a set of linear equations if we have, then if we want to solve it, the important condition that the matrix A must satisfy is it should be non-singular, means determinant of A should not be 0. right. If the determinant of A is 0, then we cannot have unique solution of this system, right, that we all know. Now, let us try to understand. So, essentially we also, if we take a system like this, here also we are doing essentially same thing. We are solving Ax is equal to B, where A is equal to the stiffness matrix, B is equal to the load vector, and the x is equal to the displacement, the unknown displacement field, right. Now, but if you calculate the, if you see what is the determinant of the stiffness matrix, then you will see that this determinant is 0. But the condition for a system of linear equations to be solvable, to have a unique solution, the determinant of the coefficient matrix should not be 0. The matrix should be non-singular, should not be singular. But in this case, the stiffness matrix is singular. Not only that, if you take individual element stiffness matrix, member stiffness matrix, all these matrices, if you look, they satisfy, they are symmetric, they have all the diagonal terms are positive. But in addition to that, one important feature of this stiffness matrix you can see is all this determinant is 0. So, if you take determinants of k, you will get 0, determinant of k2 you will get 0, similar determinant of k3 will get 0. Okay. If the determinants are 0, then what does it mean? And not only that, when you assemble the stiffness matrix is also 0. If the determinant of the stiffness matrix is 0, it means that we cannot have the solution, we cannot determine the solution uniquely. The expression that we have here, that stiffness into displacement is equal to force, in this representation which represented this entire truss, we cannot have a unique solution to this system. Now, what does it physically mean? You see, once Ramanujan said, Srinivasan Ramanujan said that an equation means nothing to me unless it expresses a thought of God. Well, I would like to interpret this expression in this way, that behind every equation has a story. Every equation tells you something. Every equation tells you something about some physical process. Blindly knowing the equation without understanding what story it tells, what is the underlying physical process, it is meaningless. Okay. So, when I say that representation of the mathematical representation of the system is equal to force, stiffness into displacement is equal to force, and then the stiffness is singular, then what does this physically mean? If you recall, in the first week when we were reviewing some of the concept of structural analysis 1, I showed you this slide. If we take a system, say for instance this one, and if we apply a force, then if there is no constraint in the system, then it is unstable, right? And then, but if you provide some constraint, then what happens? If you don't provide a constraint, this is a two-dimensional object. This two-dimensional object has 3 degrees of freedom, 2 translation and 1 rotation, and in 3 dimension it has 6 degrees of freedom, 3 translation and 3 rotations. But then if you constrain them, then you are reducing the degrees of freedom, and once you do that, means the structure is not free to move. Structure has lost its freedom to move. Some of the degrees of freedom the structure has lost, and this makes the structure stable. Okay. Now, if we see this expression, in this expression, this is the stiffness matrix, which is the property of this structure, the property, material and the geometric property of the structure, right. In this case, in this stiffness matrix, we have not given any constraint. If we don't give any constraint, then the structure is unstable, right. In order to make the structure stable, we have to we have to produce, we have to reduce some of the degrees of freedom of the structure. We have to provide some constraint, and that is exactly we have to do here as well. Okay. So, what constraint we have, that information we have to put, we have to substitute that information in the stiffness matrix. If you do not substitute that, if you do not give this information, then this stiffness matrix is for the entire structure, assuming that every node had all the degrees of freedom. But if every node has all the degrees of freedom, means the structure is not stable, and this is manifested by the fact that this stiffness matrix is singular stiffness matrix, means we cannot have a unique solution. So, we cannot have the unique solution. The physical interpretation of that, the physical the physics or the physical process behind this is the structure is unstable in this case. Okay. So, in the physical problem, we have to make, in order to make the structure stable, we have to substitute, we have to put the constraint, we have to reduce some of the degrees of freedom. Exactly here also we have to do the same thing. So, if your model is correct, then whatever you observe through your model, through the mathematical representation, you should be able to observe physically as well. If you do not do that, then probably there is some problem, there is some something wrong in our model. Okay. Now, so we have seen that this is singular, and the physical processes, it is unstable, which is very consistent. Now, let us see how to enforce this boundary condition, how to provide this information about the constraint, and this is exactly what we are going to do in this class. Okay. Now, you see, let us see what are the information that we have about this problem, Now, if I draw the you see this end is fixed end. So, in this case all degrees of freedom are there is no degrees of freedom at joint A. Okay. So, in this joint U5 is equal to has to be equal to 0 and U6 is equal to 0. U5 and U6 are the degrees of freedom at this joint. Okay. Now, with the joint C has degrees of freedom in this direction, but joint C is the roller support. So, it does not have degrees of freedom in the vertical direction, and therefore, the vertical direction degrees of freedom is U4. So, therefore, U4 has to be equal to 0. So, this is the information about the displacement we have. Okay. So, U5 is 0, U6 is 0 and then U4 is 0. Okay. So, suppose if we defined U, which is U known, K for known, then U known are U5, U4, U5 and U6 suppose, and what are these values? These are 0, 0, 0. Okay. So, this is U known. Now, what is U unknown? Then we define another U, which is U unknown, U small u, which is equal to then U1 is unknown, U2 is unknown and similarly U3 that is also unknown. So, we need to determine what is this unknown displacement. Now, let us see what information we have about the forces. Now, the external force, if we have a vertical force F at joint B. So, P2 will be minus F because the force is in the opposite direction of 2. Okay. So, P2 is minus F. We do not have any external force in this direction. So, then P1 has to be equal to 0. Similarly, we do not have external force in this direction, we do not have any external force in this direction. So, therefore, P3 has to be equal to 0. Okay. But then we do not know about P5, P6 and P4. There are no external forces, but since they are constrained, there could be some support reactions as well, which will be equal to P5, P6 and P4. So, what are those support reactions? We do not know. So, P5, P4 and P6 they are unknown, and P1, P2, P3 they are known. So, similarly, similar to U, if we define P which is known, that is equal to P1, P2, P3, P1, P2, P3, which is equal to P1 is 0, P2 is minus f, and P3 is 0 again. And similarly, if we define P unknown, which is equal to P4, P5, P6. Okay. Now, what information we have? Now, what information we have is, we have this information, we have this information, this is, and we have this information. With this information, we have to determine what is this and then what is this. Okay. Now, with the information from this and this. Okay. Now, what we do now is, we will see how to find out how to get this information. Once we get this information, then how to get this information and the subsequent other information that we need, that we will discuss in the next class. Okay. Now, so go back to our stiffness. So, this is P and this is total P and total U, and in this total and total P we have just two. This part is P known and this part is P unknown. If we see, this part is P unknown and this part is P known. Okay. And then this part is U unknown and this part is U known. Okay. Here we can see this part is U known and this part is U unknown. Okay. Now, if I take the stiffness matrix, this is the expression of stiffness matrix. Okay. Yes, this is 1, this is fine. Okay. I will just keep it here. Now, similarly, what we can do is, so this is, and you partition the load vector as well as the displacement vector, and if you partition it, it is U unknown, it is U known, and then P unknown, this is P known and this is P unknown, right. Now, similarly, once you have partitioned this, now in this case it is a consequence, it is a coincident that first 3 displacement, first 3 degrees of freedom are known and these last 3 degrees of freedom, first 3 are unknown and the last 3 are known. But for some structure, it may so happen that your known degrees of freedom and the known loads are not serially numbered. So, in that case, we have to rearrange the corresponding rows and columns of all these load vector, displacement and the stiffness matrix to get this number serially. We will do some example towards the example like that towards the end of this week. Okay. Now, similarly, let us partition the stiffness matrix as well. Now, we partition the stiffness matrix as well. Okay. Now, suppose name this is K unknown. Suppose this is K unknown, and then we partition this as, suppose this you name it K known, and then it is Ku. Why I am writing Ku and Kkk, it will be clear shortly, and then you have take it say K Uk, and then we have K U. Okay. Suppose this is partitioned like this, and if it is partitioned like this, then what we can write that, there is something. Okay. What we can write is as this. You see, say P k, P known, P unknown, that is equal to stiffness matrix and U unknown and U known, and this is K K K K K U K U K and K K K. Okay. Now, where K K K is equal to, if we K K K is equal to this part, K K K is equal to your K K K is equal to this part, this the entire part, and K is another part, this is another part, and this is another part. Okay. Now, so we have this, right. Now, if we have this, then can we write P k is equal to K k into U k plus U U plus K K U into U k. Similarly, P u is equal to unknown is equal to K U K into U U plus K U into U k. Okay. Now, from this we will come to this. So, there are equation number 1 and equation number 2. Okay. It is all these expressions are, this is a matrix expression. This is a matrix, these are all matrices, stiffness matrices, partition stiffness matrices. This is known displacement vector, unknown displacement vector, this is unknown displacement vector, unknown displacement vector. Okay. Now, let us consider the first equation today, and we will see how to use second equation, what is the use of second equation in the next class. Okay. Now, the first equation is, so let us write it again. So, P k is equal to K U U and then please plus K K U, this is matrix, and U k. Now, in this we have already seen this is equal to 0, this is equal to 0, is not it, because U k is equal to, if you remember, U k is equal to, that is U 4, U 5 and U 6, which are is equal to 0, 0, 0. So, if it is this, then essentially we are left with this expression. Okay. And we know that this expression, and in this expression what we know? We know that P k is equal to 0 minus f 0 and U is equal to your U 1, U 2 and U 3. Okay. Now, let us solve this equation. If you solve it, so this equation is, so we have we have 0, then minus f and 0, that is the okay, let us, the matrix will be A e by if we take that matrix, this is half, you can check it, minus 1 by 4, 0, 3 by 2 and then root 3 by 4. This is minus 1 by 4, root 3 by 4 and then 5 by 4. This is the stiffness matrix, the first part of the stiffness matrix, and then this into U1, U2, U3, that is equal to 0 minus f and then 0. Okay. Now, in this expression you check your this stiffness matrix is not singular. Now, why it is not singular? Because you have already given the constraint, and so this stiffness matrix, the reduced stiffness matrix, or the after the partition the stiffness matrix you have, this stiffness matrix is with the information from the global stiffness matrix, you applied constraint and reduced the stiffness matrix, the global stiffness matrix to this. So, when you write this is the stiffness matrix, this is the stiffness, it means already you have enforced the boundary conditions, and that is why the structure is now stable, and which is the it is in this expression that is getting manifested as it is not a singular stiffness matrix. Now, if you solve them, what we get is U1, U2, U3 is equal to U1 is equal to, you can check this solution, 0.1433 F L by A, U2 is equal to minus 0.7500 F L by A, and U3 is equal to 0.2887 F L by A E. So, this is the solution of the displacement. Okay. Now, once we have solved for the displacement, next is we have to determine what are the support reactions and the member forces. Okay. So, support reactions and the member forces, how to determine them, we will discuss in the next class. So, please the partition here, partition of the stiffness matrix is a very important step, and please we can demonstrate only the process through 1 or 2 example at the most. If you look at books, there are many examples given with different numbering, different boundary conditions, different number of members, and you see those examples, you yourself try to find out the member stiffness matrix, you try to assemble them and then construct the load vector and the displacement vector and solve them. And if you can do that, then probably some of the concepts will be clear. So, we will stop here today. Next class we will start with the same global stiffness matrix and partitioned global stiffness matrix, and then see with the information about the displacement, unknown displacement that we have already determined today, with that information how to determine the support reactions and the member forces. Okay, I will stop here today. So, see you next class. Thank you.